The research I'll be discussing today is applying mining schemes to software fault prediction, a proposed approach aimed at test cost reduction. This research was conducted and authored by the two authors displayed here, Hegigi and Disafoli and Farhad Mahad. So the initial problem statement of software faults cause prolonged development time, extended maintenance needs, degraded performance, data discrepancy, and security risk leading to breaches. These factors strongly contribute to customer dissatisfaction and loss of revenue. Now, the main reason for this is because it takes extensive manual processes and unit testing. Both of those are very cost intensive, requiring lots of FTEs associated with them, as well as time and often a lot of rework. A secondary problem is the attempts to automate through the use of AD mining algorithms for feature extraction, using machine algorithms and classifying good code or bad code according to bugs is really inaccurate at the time of this research, and there was the opportunity to improve it. At the time of the research, it was not sufficient for commercial use or very critical production environments, so the researchers wanted to be able to enhance the performance using common techniques, but bettering the accuracy results of actually detecting true bugs and reducing the false positives of good code being identified as bugs. So currently, the manual code limitations is several factors. One, humans read code very slowly. It's much slower than automating through machine learning or any kind of automated process that would create a lot of efficiencies and speed to production deployments. The process is prone to error. Humans, especially when reading somebody else's code all day, every day, they tend to become fatigued and miss some simple mistakes and just lose efficiency or accuracy over time due to the fatigue problem. And then typically code reviewers are not as skilled as the developers. So it's usually an entry-level position, sometimes held by interns, where it's the stepping stone into the full-time developer role. So they're reading code that's more complex than their skill level allows them to evaluate at that point in time, which causes other problems in identifying bugs or being able to give remediation steps to make the code simpler and less complex. Complexity not only plays a role in introducing bugs to deployment rollouts, but it also makes the maintenance of code in the future and future development efforts more difficult and more prone to bugs as it becomes complex over time. The other way that it's typically done is through unit testing. Unit testing has its own set of problems. A couple of them are, all test cases have to be identified up front before coding begins so that you can have quality assurance and ensure that the code meets test cases. This is a difficult proposition in the waterfall methodology because, it could be very resource intensive with FTEs and specific teams dedicated solely to the creation of these test cases, running them, evaluating them, creating new ones every time the code requirements change. And it makes changes difficult. And in Agile, that becomes even more of an issue because Agile wants to move and make changes quickly. Requirements often aren't known up front, and creating test cases for unknown features that are identified during the development and agile processes and daily stand-ups really cause issues, and the testing, unit testing actually slows down the production pipelines. Beyond those limitations, in the agile flow, those really to the manual code reviews in the unit testing, they're based off of a paradigm created by Jerry Weinberg of NASA's in the 50s and 60s. And it really doesn't reflect the Agile manifesto and the way things are created, which was, from 2001. So we're still talking quite some time ago. And as development workflows and pipelines increase efficiency and the speed to production deployments increases, these typical manual type processes using manual FTV code reviews and unit testing really starts to slow things down. So there's definitely a need for an automated process. So, looking and trying to articulate through visuals here, in a typical waterfall, you have your requirements, design, your build, and at this test phase, if a bug is detected, you have to go all the way back to the requirements phase again, which is a significant setback. This could be weeks or months between requirements and actual testing again. Now, in an agile process, you may not have the requirements, but you certainly identify features and that you want to have built out, and you still have at a testing phase a revisitation, at least to a design or a coding build piece before you deploy. So having something along the lines where every pull request does a complexity check and a bug detection check really eliminates a lot of the rework needed, because it could be very small incremental changes that are introduced that take minutes opposed to days, weeks, and months to fix issues detected. So the approach used in this research was to use the NASA software defect JM1 dataset. This is publicly available on Kaggle. I provided a link here if anybody wants to go and look at the data set or use it themselves. Data set consists of 22 different columns, 10,885 rows, and the true meaning that there were bugs detected is 8,779, so 80% of the record set itself, and 2,106 rows, little over 19% false, that they were good code. And the reason why I was so heavily weighted towards bugs is because you really need to teach the machine learning algorithms what a bug looks like, so it can identify it when it's evaluating code through its prediction and classification that it hasn't seen before. So just creating a pandas data frame and running the head command on it, this gives you an indication of what the data set looked like. It's all numerical so that you have consistency being fed into the machine learning algorithms. And I'll get into a little bit later what these column headers mean and what the feature extraction is, and what the best features are for training the ML algorithms. And you'll notice here on defects, this is represents your 80-20 split really of true to false, and all the data is labeled to do a supervised learning process. Supervised learning process is when you have labeled data so that the machine learning algorithms knows when it's predicted something correctly or not based on this label, and that allows you to fine tune the algorithms and get them better. So the two different ways to determine code complexity used in this research was McCabe and Halstead metrics. So the Halstead metrics were created in 1977, and they really are looking at procedural coding and not object-oriented program. They won't work on there, at least not with any accuracy or usefulness. So that was one of the things used in here, and it's a little bit of a fault to try to include this in the research at this point in time, the way software is developed, but there are some applications, robotic operating systems, IoT devices, some very specific niche needs where this could be useful. So I believe that is the intent of including it in here. And I put some notes in here about how it's actually calculated and used. The other one, which seemed to yield the best results, particularly for modern programming paradigms and object-oriented methodologies, is McCabe. Even though it was created in 1976, it works with object-oriented program. The calculation, which we'll see in a second here, primarily the cyclomatic complexity measure, actually looks at software components and connected components, which would represent object-oriented program, additional libraries and classes that would be used in there. And it accounts for that in its complexity metrics, which is crucial when you're looking at object-oriented program, where there could be a lot of lines of code and loops and decisions being made in some of these components that are in other classes. So the cyclomatic complexity works as follows: taking the simple little bit of source code with an if statement, you'll see that the equation is edges minus nodes plus 2p, where the p represents the connected components, so a class or a library or something else being used by this would be represented by p. And we see the breakdown here. P actually is 1 because this does not call out to any other libraries or any classes. But you will see that there's some additional edges and nodes for this if statement. So that's accounted for in the measure. And that's where you get additional complexity for that. Something linear would equate to a 1. So if you didn't have the if loop or any kind of other loops or decision points, and it was a complete linear code, it would equal 1, which is the least complex. This one here is a 2 because this adds some additional nodes and edges coming through here. So we can count the edges 1, 2, 3, 4, 5, 6, 7, and the nodes 1, 2, 3, 4, 5, 6, 7 as indicated here. And the formula is your plus 2p, so that's where you come out with 2. Looking at something a little bit more complex here, 2 for loops. This is represented by these additional nodes and edges here, and you'll see that the complexity is 3, so the formula does accurately represent the fact that this is more complex, which leads to more opportunities for mistakes to be made in the coding logic here. You have several different paths that the code can take towards execution before it exits at node 7 here. This is just I won't go through all these, but this is just a brief breakdown of the column headers if anybody wants to review the data set. And you'll see a lot of references to McCabe's complexity. So cyclomatic complexity is represented by column 2 here, essential complexity, which is very similar to what I just demonstrated. Lines of code factors in as well, and that's typical. The more lines of code you have, the more difficult it is for those unit testing or manual processes, but also the better opportunity to introduce mistakes or errors or bugs into the code. So for this, getting into the machine learning techniques utilized, bootstrapping, bagging, and ensemble were the typical ways that the researchers were able to improve the accuracy of machine learning for bug detection. Just for a quick breakdown, bootstrapping is really when you split the data out and you use some different test samples to train the machine learning. So if you have an algorithm that doesn't quite have accuracy and it's missing certain predictions on certain types of data, you take those rows, you combine them into one data set, and then you retrain the algorithm on the ones that it's actually predicting wrong and having difficulty with to improve the accuracy across that data. And in theory, then when those problem areas or problem data sets are introduced back into the bulk data set, the algorithm will perform better on those because it was trained specifically on those to help enhance accuracy. Bagging is taking your data and randomizing and splitting it into multiple data sets, and then creating a classifier for each data set, training it on that data set. And then when you run your predictions, you run them through each classifier that was created that corresponded to a particular data set. And then those results, where they have predictions, whether it's a bug or not, um, it'll take the same bit of code and run it through each one. And you may have 5 different classifiers. 3 may say it's a bug, and 2 may say it's not. When it gets to ensemble, that's just a voting process where the code will look at the results of each classifier and say, well, we had 3 that said it was a bug, 2 said it wasn't a bug, so therefore it must be a bug because there's a higher probability based on the results. So this really takes the power of multiple classifiers trained with different variables and settings, and allows them to work together to give better results. So looking at the flow, you have your data, you split it into 3 bags in this example. You could have n amount of bags. You have your classifiers, you could have the n amount of classifiers. They all spit out a prediction for a particular piece of code fed into it. You have your voting, and then you have your final classification based on that voting. So it's a pretty simple concept, but very powerful in the results it provides. So the researchers in here, rather than writing code from scratch using scikit-learn, TensorFlow, PyTorch, or any of those software development environments for machine learning, they used Weka. It's an open source machine workbench, and it basically allows you to take algorithms, train them on data, and then be able to get results. It's great in a scientific setting if you want to try a bunch of different algorithms, not spend the time coding. The one downfall of it is you really can't fine tune the hyperparameters of the machine learning algorithm. It's not very tunable, so that tends to reduce the accuracy you can gain out of these out of the box, and you're really just dependent on the algorithm itself for accuracy. But J48 decision tree is one of the key ones used. It used information gain, which is just basically when it makes a decision that splits the group, the classification, in this case, bugs or not bugs, the best possible way, that's when it knows it made a good decision point, and it tries to get the biggest split first and then make additional decisions as it goes down the line. Through decision points. So the first one might say, hey, I was able to get 90 bugs detected and only 10 not, and that's a good data feature to split on. So it's really looking to split on features, which are the columns in the data set itself. So accuracy measured in here, and where this becomes important is where the classification algorithms are compared to each other. So just a couple quick things. ACC, as you'll see in a lot of the results, that's the accuracy of the predictions. And this is the formula, and it's true positives plus true negatives divided by true positives plus true negatives plus false positives plus false negatives to give you what your accuracy is. Your true positive rate, sometimes known as sensitivity, your false positive rate. And then 2 key things that we're really going to be talking about that summarizes the results is the receiver operator curve. And this basically takes each classification algorithm, summarizes the results, basically the ratio between the true positives and false positive rate, and puts a point on a graph. And that'll tell you, so if you take one classification algorithm, say linear regression, you set your threshold for each run of the algorithm through the data, and you get different results, and it'll map these across this curve. And then you can look for the point that's in the upper left-hand quadrant, and that'll tell you which hyperparameter fine-tuning or which threshold on, say on a linear regression that you picked is the best. And that's your best, most accurate setup for that particular machine learning algorithm to run through the data. And then what the area under the curve does is it takes these receiver operator curves and it compares each curve from each machine learning algorithm you have. And the one with the biggest area under the curve, meaning it has an arc going to the top left-hand quadrant, will be your best actual algorithm overall, when you average all the different settings you can have for being accurate in representing the predictions there. So that helps you distinguish between all the different available machine learning algorithms. So a little breakdown of this is to actually be able to create a ROC, you use what's called a confusion matrix. So you'll have your predicted value. And if it's a fault, your true positives are here. If you predicted wrong, your false positives would come here, which actually fall under the actual not a fault. And then your predicted not a fault true negatives that you got right are here. The ones that you got wrong were here. And it takes these, and this is how it does the calculation for the receiver operator curve. So this confusion matrix here, which when you have a lot of these, it becomes difficult to compare side by side, gets graphed on here. And this one would represent this point right here. So we predicted 4 that were fault, not a fault. So it was kind of a 50-50 split. And you see the linear line would fall right through here, where its accuracy was about 50%. So that would be that point on the line. If we had another algorithm where we changed the hyperparameters or the threshold and we did a little bit better, we predicted 4 were fault, but we got 2 wrong, and we predicted accurately that 2 were not a fault because our 2 columns line up here. This is the intersection of these 2, so that shows you we got it correct. That point would be graphed here, showing about 75%. So we actually did better here. And you see how this starts to form a line. So we do this again, we have different results. It graphs another point on the line, and this starts to form the receiver operator curve, which then we can do an area under the curve calculation to actually compare algorithms, but it also allows us to see which one of these points does better. So depending on if you're want to get the best possible accuracy on identifying positives or the best balance between identifying positives but not falsely identifying something, you may pick this or this. It depends on the use case. And then once you get to the area under the curve, you'll see that we might have these points identified for one algorithm here, identified by purple, another one identified by blue. And you can see that clearly the one in purple performed much better just visually by looking at this graph, but these are also converted into numbers for ease of use on a spreadsheet like fashion for the researchers, so you can compare tens of thousands of these at a time. So getting to the results now, we have our accuracy and we have our area under the curve. Each one of these identifies a different data set that was run against the particular algorithm. So in this case, we have 5 different data sets that it was run on, and you see the numbers are different. So on the different data sets representing, the fact that the algorithms weren't overtrained against a certain data set, and they encounter things in real life data that they might not have seen in their training set. But we could see using the bagging technique, it had the highest result here, circled at 0.915. And it has also had a fairly high average across data sets here. And this was the area under the curve score. So that's really taking that average across all the different hyperparameter settings. Now, bagging at the time of this research was really conducted on that J48 decision tree algorithm, but now with scikit-learn and other libraries, you could actually apply the bagging technique to any machine learning algorithm that you want to utilize. But back then, especially in Weka, you could only use the bagging itself, which was that decision tree. And then these other ones didn't have that ability to use bagging or across them. coming back here quickly, there was another algorithm called PART that yielded a little bit higher area under the curve result on this data set. But if you look across the other data sets, its average was lower than what was, you know, gained by the bagging itself. So, the top score might have been a little bit higher, but the average across there for bagging was 3% higher. So the researchers felt that was a better representation of something that would be accurate to be able to use in a commercial use case. So, looking to critique the techniques, the approach wasn't really that unique. This was something that was done before, and the authors were really just trying to improve upon what was done by others. And I felt like that wasn't very unique, but also the tooling they used prevented them from really achieving their goals and improving the accuracy. 80% average across there. I felt like that could have been much improved using a standard library like Skylearn. They stated that naive Bayes was the most popular algorithm for fault detection, but they weren't able to actually apply bagging to that because they used the WCAG tooling instead of coding it by hand and being able to apply bagging and boosting and other advanced techniques to naive Bayes, which may have actually improved the accuracy far beyond what they got from just the WCAG bagging algorithm. The other thing is the data set was quite small. Bagging, when you're splitting the data up, especially as much as they did, it really requires a large data set, and 10,000 records is quite small for that. So they might have been able to get a lot more accuracy if they would have acquired bigger data sets or combined some data sets out there, which would have gave diversity of data in there, where the feature extractions might have been a little bit different as well. But overall, it opens your eyes to other techniques that can be used. And there's a lot of things done with static code analysis and other security pipeline tooling to detect security flaws like command injection, SQL injection, and other things that could open up security holes in software. But when you talk about bug predictions and fault tolerance, this could also be applied to security. One of the big things or uses I see can be used for security is looking at infrastructure as code. The more complex infrastructure code becomes, the bigger the opportunity to have mistakes or errors in there that could lead to vulnerabilities in the actual configuration of these cloud resources. So applying this technique to infrastructure as code and looking through things like Terraform code could be tremendously valuable for people in the future. So this concludes my presentation on the research conducted. Thank you.